Okay, directions here at the top of the page say today each team will find the area of a shape and present their work to the class. Each shape is a regular polygon. Remember, that means all sides are congruent and all angles are congruent. Well, each team will not be doing that today. I will be doing it for all 6 shapes. We've got 3 on the front and 3 on the back, and they are all regular polygons. So let's get going here with this first one. We got a square. And this one actually says, besides just the area, we're supposed to find the area and the exact side length of the square. Okay, so the first thing I notice here is I'm given this dimension, which is 6. And I know that the diagonals of a square cut each other in half, and I know that they are congruent, so both of those pieces have to be 6, and I have to find this side length S right here. Well, I also know that the diagonals of a rhombus, which is a square, are perpendicular, so that means what I have there is a 45, 45, 90 right triangle. From the 45, 45, 90 rule, I know that if I have a triangle that meets those criteria, the hypotenuse is going to be the leg times root 2. So that means this is 6 times root 2. Side length, 6 times root 2, and that is the exact side length. Okay, so now we have to find the area for the square. The area of a square is side length squared. So that's going to be 6 times root 2 squared. Let's see, 6 squared is 36. Root 2 squared is 2. 36 times 2 is 72. So we're already done with the first one here. We got 72 square units for that square. Moving on. I mentioned on the previous slide that we have a 4-step procedure for finding the area of a regular polygon, and you're going to see that procedure now. That was the first example there. Really wasn't required to step through that procedure, but for this regular hexagon we will. And don't forget, for a hexagon we have 6 sides. Okay, so we got a regular hexagon here. First thing I'm going to do is I'm actually going to split this bad boy up by drawing in, connecting several of the vertices so that I can show that this hexagon can really be thought of as 6 different triangles. So in the beginning, when I mentioned I was going to talk about a central angle, this is the angle I'm referring to right here. I'll call that letter A. So in this hexagon we have, let's see, there's 1, 2, 3, 4, 5. There's 6 of those central angles. So 6 times A has to be equal to, well, if I take one complete revolution around, I have 360 degrees. So 6 times A has to be 360 degrees. I do 360 divided by 6, and I get that A equals 60 degrees. Okay, so we've identified this thing that I'm calling a central angle, and that has a measure, in a hexagon it has a measure of 60 degrees. The next thing I want to talk about is what I'm calling a central triangle. Okay, and that's this triangle right here, and you'll also see that there are 6 of those in this hexagon because we have the one that I just highlighted plus the 5 others that go around the hexagon. So what I want to do now is start to analyze that central triangle, and I'm going to do that by dropping a perpendicular from that central angle. If the central angle is 60 degrees, I know that this angle here has to be 30 because that splits that central angle in half. I also know that this little piece right here is 4 and this is 4 because these two have to be congruent. So now I'm in the step of analyzing that central triangle. And I know that the area of that central triangle is 1/2 base times height. Well, I have the base as 4, but the height I don't have just yet, unless I recognize that this is a 30, 60, 90 triangle. And the long leg, in this case, that's what I'm calling the height. The height is going to be equal to the short leg times root 3, or 4 root 3, and that's again the 30, 60, 90 rule. My dogs are very, very excited about the 30, 60, 90 rule. if you can hear them in the background. Okay, so now I can find the area of that central triangle. It's going to be 1/2 times the base, which is this whole dimension here of 8. Be careful, it's not 4, it's 8. And then times the height of 4√3. So when you go ahead and multiply that out, you're going to get 1/2 of 8, which is 4, and then 4 times 4√3, which is 16√3. And that's approximately equal to 27.713. Okay, so now let's talk about the area of the hexagon. Well, the area of the hexagon is going to be, I have 6 of those central triangles, so it's just going to be 6 times the area of that triangle, or 6 times 16√3. That's equal to 96 times the square root of 3, which is approximately equal to 166.28 square units. So there's our answer for the area of that regular hexagon. Now let's jump down here to the regular nonagon, also known as the nonagon. Remember that this means it has 9 sides. Be helpful if I put a 9 there. And let's go ahead and see what each of these central angles and central triangles are going to look like. I'm not going to draw them all in. I'm just going to draw a couple to help us organize our work. Okay, so this angle right here, that's going to be my central angle. I have 9 of them. 9 times A has to be equal to 360 degrees. That means that A has to be equal to 40 degrees. So that central angle of 40 degrees, when I go ahead and drop a perpendicular down here, and now I'm analyzing this central triangle. When I drop that perpendicular down here, that means that each of these angles up at the top are going to be 20 degrees. So let's take a look. I've got the angle of 20, and then what I haven't is the hypotenuse of that right triangle on the left there. And when I say right triangle, this is what I'm referring to, this right triangle right here. I have the hypotenuse, which is 11. So what I need to do is I'm going to label some pieces, parts here. I'm going to call this X. I'm going to call this H. And I want to remind you that the base of that central triangle is going to be 2 times X. Okay, so let's now analyze that central triangle. And we're going to do that by first looking at the leg. Okay, so I have this 20-degree angle. I have X, which is the opposite leg, and I have the hypotenuse, which is 11. So I think I'm going to use the sine ratio there. That means X equals 11 times the sine of 20 degrees, which is approximately equal to 3.7622 units. We're going to do the same thing for the height, except this time it's going to be a cosine ratio. And that calculation gives us the approximate value of 10.3366. Okay, so I think I have all the dimensions I need to calculate the area of that central triangle. Let's go ahead and do that now. The area of a triangle is 1/2 base times height. So that's going to be 1/2 times, remember that's 2x for the base of that central triangle, times height. So I have 1/2 times 2 times 3.7622 times 10.3366. And that gives us an area of about 38.888 square units for each of those central triangles. Some of you may notice this. We've got 1/2 times 2, and those actually cancel out. 1/2 times 2 is 1. So you could just do this value times this value. Okay, now let's go back and talk about our final polygon here, which is a regular nonagon. And that's going to have an area equal to 9 times the area of the triangle, or 9 times 38.888. And that gives us an area of about 349.99 square units. Oh heck, let's just, let's call it what it is. It's about 350. So it's about 350 square units. All right, that's it for page 1. We're going to shut it down here and pick up the rest of this lesson in part 2.